Florian was competing with me and didn't know. He didn't know that. And it was in 2020. And then wow, Florian, I didn't know him. I looked for Florian, the papers and the Google Scholar. Florian in 2020, he had like 18,000 citations. So it is a rock. And I think you're gonna spend a good time with him today. This is why I was trying to define with you about what would be the best strategy, having one talk or two talks. And I think they prefer one talk, cough break, and if we can resist anymore, you can go to the second one. Okay.
Let's see how they feel, how everyone feels afterwards.
So let's try this one. The
Perfect.
First one first.
Let's do the first one first. Cool. Thank you for the kind introduction, Tiago, and thank you all for attending and being here and suffering through the short blackout. And I realize I'm between you and coffee, so I guess Tiago told me I first have to make you suffer before you get coffee. But let's make it entertaining. So quick acknowledgements to all my collaborators. One thing you have to know, almost everyone in my team is rock climbing. It's like a prerequisite if you want to join the team. Those are all the people that contributed, except for one other professor. I couldn't convince him, so he's a diver. But so this worked mostly by my first student that got this started in 2019, Jeremy, and then it went on over a few generations. You may see some of those at the CDC.
I think you need to try this one.
Should I use a microphone? Sure. Is that better? Okay. Good. I'd like to kick some things off on data control and share some high-level perspectives. Is that working? Fine? Okay. So it's a very, let me say, nowadays hot topic across different fields, control, reinforcement learning, signal processing. And on every contemporary topic, people have their opinions, right? So everybody's entitled to their opinion. And since I'm on the stage, I'll just blur out my opinion now. So across science, we see in all disciplines an increasing importance of data-centric methods in academia and in industry, right? I would like to think it's because of us, because we're so cool, because we have so many new methods, algorithms, tools, optimization, statistics, and so on. But that's not really true. If you're really honest, the reason why people love data science so much is because we have brute force. That's the simple answer, right? We nowadays have more data, we have faster computers, we have more storage, everything is better, and we can brute force just works. That's the simple answer. And of course, there's a general frenzy surrounding machine learning, data science. Everybody wants to have a part of the pie. And everybody has their opinion on that, like that's just a hype cycle, will go away, or that's the biggest thing ever, that's the second industrial revolution, anything in between. So everybody has the opinion, but you cannot ignore it. It just works, right? And so one question I asked myself about in 2018 or so is this also true in my field, my native field of control engineering? So is there room in control for data science, for machine learning, for data-driven control? And I think the community has made up its mind. So I'd like to quote one of the statements in the Control Systems Roadmap. So in about 2023 or so, about 200 control scientists got together in Stockholm and wrote this big manifesto. And one of the chapters starts off with saying one of the major developments in the entire field over the past decade, and one of the most important going forward, is the cross-section of machine learning control. Like written down, signed by 200 people leading in the field. So I guess it's official. It also, puts control in the spotlight, which is nice, because normally control people are like the nerds in the building somewhere that work out their proofs nobody cares about. But now suddenly we get a lot of attention. So for instance, a colleague of mine made the cover of Nature, essentially using a combination of reinforcement learning or data-driven MPC. And also within the control community, we dedicate various special issues, conferences, events, workshops to this topic. So I guess it has arrived and is mainstream nowadays. So what's the scientific landscape? I guess we should first acknowledge this is not new. This started long before my time. Maybe the earliest reference I can point to was sometime in the 1970s when Carl Ostrom developed auto-tuned PID controls that would just, trigger the system, excite it, collect some responses, and then auto-tune the PID parameters, and it would do so adaptively. And so there's a long history in SysID and adaptive control, but also on the other side in computer science under the name of reinforcement learning. And I should say the research is very vast and fragmented. That is, if you try to put things into bins, it's very hard to cluster them. You know, people are doing a million different approaches, and it's hard to cluster them. So one classification, which is very old, but still useful nowadays, is that just of, is your design direct or indirect? That is the following. Say, you are the brain here. You want to design the algorithms. Let it be an optimization or control algorithm. You interface yourself with a system that you don't know. Let's keep it simple. Say it's a black box. And there's two options you have. Either you collect data from the system, and then you build a mechanistic model of the system. Yeah, it could be based on first principles or just using numerical system modification, just some vector field, for instance. That's the indirect model-based approach. The other one is the direct one, that you just search for control policies which are compatible with the data you have seen. You don't have any model in mind, you just say, I want to be compatible with the data. And those are still a useful classification nowadays. Again, goes back to the 70s. So if you put this a little more mathematically, the direct data-driven control problem can be phrased very simple. You collect inputs and outputs, U and Y of your system. You're interested in minimizing control costs depending on inputs and outputs. Subject to the trajectory that you search over is compatible with the data you've seen. So if you see superscript D, it means data. So that's a very lean problem formulation. Okay? So search over inputs and outputs compatible with the data you've seen. Of course, it's hard to make this precise. What does it mean to be compatible? But if you stay with me for a few minutes, then I'll explain to you, at least for some system classes, how you can do this. So that's a direct approach. The indirect one you could abstract as a so-called bi-level nested optimization problem. That is, you collect your data from the system, you minimize a fitting criterion. Think about minimizing a least square problem. Find the best, ARX parameters of a model. Subject to the model belong to a certain model class. For instance, the class of all linear time-invariant system with, say, 10 poles and 8 zeros, for example. Okay, so you first, in an inner loop, identify your model. Once you have the model, you go into the outer design. We say, now I want to search for trajectories or inputs and outputs compatible with the model that I identified. So formally speaking, what is the difference? If you write it in this level of abstraction, this is a nested bi-level two-step optimization problem, where this is a single-shot solution. Okay. So people have argued about the pros and cons of these two approaches for decades, literally for many decades. And I collected a little bit the pros and cons that people have put forward over the years. On the one side, on the indirect side, they would say, well, models are useful for design with powerful design methods, such as linear algebra. But models are also useful beyond, for analysis, system understanding, fault diagnosis, and so on. The direct approach will argue, well, yes, but some models are just too complex to be useful. Think about developing a first principle model for something like a soft robot or for a wind farm. Good luck writing down a first principle model. Even if you had it, it would be some complicated nonlinear time-varying PDE. It would be completely useless to do anything with, right? Other arguments are models are modular and easy to debug. So the design process is, step by step. You can easily debug it. But when you go to people in industry, my experience is they don't want modular individual step. They'd like to have an end-to-end pipeline. Say, just give me the algorithm, I give it to the engineers, and they tune it. So often I learned that end-to-end is actually preferred by practitioners. You can take the approach, what does system identification do? So identification essentially projects data you've seen onto a model class, so the class for linear systems of a certain complexity. Which makes sense because you trim down the class of options, but if you do the direct approach, it's very hard to inject any side information. The model I want to control has these and these properties. It's very hard to do this in the direct approach. You could also argue that identification does noise filtering, that is, removes the variance. It ideally just cuts off the noise from the data. Whereas here you have to handle noise direct in design, which is harder. On the other hand, the main counter-argument why you maybe should not use models also is uncertainty propagation. That is, when you have data that is not perfect, your model class is not the right one, you always have an error when you identify a model. And this error, you have to propagate from the data to the model identification all the way to control design. And it's very hard to do this uncertainty propagation properly. In fact, 99% of all designs is just certain equivalences. Don't think about uncertainty. So that's a big disadvantage here that has not really resolved. Whereas here it's very transparent. There's no unmodeled dynamics. You just face the data as you see it, and you can include it. And maybe a strong argument against this one is there is no separation principle. There's no theorem that tells you it is optimal to first learn a model and then to design the controller. In fact, it is not. There's plenty of counterexamples. Like in very, very narrow situations, like a linear Gaussian setup, you can make the argument that there is a separation principle, but that breaks apart immediately. So in short, these are the pros and cons people have advocated. If you're interested, there's a long discussion online. If you get the slides afterwards, you can click it. There's not a complete set of arguments, there's many more, but this is what people have been doing. So what do I want to tell you about today? I'd like to tell you about one approach we developed in around 2019. It was a very simple idea. It literally took us about 2 hours to work it out. And we submitted to a conference thinking, yeah, we'll never hear from that again. But it took off quite a lot, so I was surprised. It's still around today. The idea uses two concepts. One is from behavioral system theory, which is a very abstract branch of mathematical system theory, and subspace identification. A particular result called the fundamental lemma. I'll tell you what that is. Based on this, you can derive a very simple, extremely simple. We teach this in the bachelor. Everything I tell you about today, we teach in the bachelor in Zurich. So it's not hardcore rocket mathematics. I mean, the proofs are, but you can teach it easily. So it's a very simple method, but powerful, going by the name of DeePC nowadays, data-enabled predictive control. I guess that name stuck. I'll tell you how to derive this very quickly, and then need to add some regularizations around it to make it work in presence of nonlinearity and noise. If we get in the end, I'll tell you some recent work about stochastic behaviors, if you want to have some bottom-up stochastic approach, how you handle this. And we are applying this a lot in power systems, power electronics, building automations. That's mostly the area where we apply this to, but people also applied this in different domains, and I have a few examples for you. So there's a quite blooming literature. There's about, say, 2 to 3, maybe sometimes 5 or 6 papers every week on this topic, and for multiple years. So it's very easy to get lost. If you want to get started, I recommend a control systems article, Control Systems Magazine, a tutorial where we sort of wrote down the very foundations, not the latest and greatest and the best, just how to get started. So that's what I recommend to do. Okay, let's get into it. Behavioral system theory. I recommend you never ever read that stuff, first of all. It is completely unreadable. It has been developed by a person called Jan Willems in the late 80s and 90s in the Netherlands from Groningen. He also has textbook and many papers. And he takes a very abstract approach. He says a system is just a set of trajectories. That's the level of abstraction he works with. No models, no ABCD, no transfer functions, nothing, just a set of trajectories. So purely set theoretic approach. In particular, dynamic systems are 3-tuple, consisting of, in discrete time, the integers. That's your time axis. There's a signal space, so that's the set of all time series you can construct, literally the set of all time series. And what is sort of the behavior, if you want to the model, the behavior is just a subset of the set of all time series. That's a system, a subset of the set of all time series, or the set of trajectories the system can express. So literally everything is written at that level of generality, just a set of trajectories, and that's why it's very, very hard to make sense of the literature, to read it. And I have to say it also completely died out for about 20, 30 years until it got resurrected. We don't need the full generality. By the way, you don't have to remember any of that. It's just to show you a little bit what is in the background. We don't need the full generality. What we need is, for now, only linear time-invariant system. In particular, a system is linear if your signal space is a vector space, and the behavior, the set of all trajectories, is a subspace. So what you're searching over is now a subspace in the set of all trajectories. So that's your level of abstraction. That's a linear system is subspace. If you also want to incorporate time invariance, then you ask for every element that is in that subspace, also time shift is in subspace. Okay, so that's the level of generality. And yeah, while it is sort of elegant and nice to write philosophy papers about that, you could also argue this completely useless, right? But it turns out this is how computer science people think about control systems. So when I talk to my colleagues in machine learning, they would say, what is a system, a control system? Well, it's just a low-dimensional feature in a big data space. Like this is a control system. It's a subspace, right? Let's just say, let's search for low-dimensional features in the data we've seen. So in particular, let's find the subspace relating my set of inputs and my set of outputs. So while very abstract, it's very contemporary and very in line of thinking how data scientists think about the world, right? They wouldn't care about mechanistic models with some structure, so they just say, let's look for low-dimensional features. So the only thing you have to remember from that slide, there is this behavioral system theory. I recommend you don't go into it. But what you should remember is that a linear time-invariant system is just a shift invariant subspace. Okay? So you just go into your trajectory set and you characterize that subspace of trajectories. And how you do this is a little bit up to you. You can use models, like state space models or whatever, to characterize subspace, or you just use raw data to characterize that subspace of trajectories. And it turns out people are very busy doing that. And let me present you just one main result from that literature. I mean, it's a result that we proved after the literature, sort of to clean it up a little bit. But it really goes back to those guys. It's called the fundamental lemma. And when I first read a paper by Willems referring to his own result as the fundamental lemma, I was sort of cracking up, like, why would you call your own result the fundamental lemma? But believe me, it is a very, very powerful and simple thing that deserves the name fundamental lemma. It goes as follows. You have a black box. You collect input-output time series from the black box. Say, set of all inputs, U living in Rm, UD, and YD living in RP. That by itself will not help you much. You need to make some assumption in the black box. So let's assume it is a linear time-invariant system, and you need to give yourself some complexity parameters. If you just say it's linear, it doesn't mean anything. It could be linear infinite dimensional. That won't help you. So you need to restrict the complexity. Particularly, give yourself an upper bound on the state space order of that system and an upper bound on the lag. What is the lag of a system? It's how many time steps you have to go backwards in time to recover the initial condition. Single input case, L and N are the same, otherwise they're different. And then that fundamental lemma essentially goes after how can you characterize now the subspace of trajectories. Normally, if I ask my bachelor students, say, how do you characterize subspace of trajectories, they would write down something like this. Say, write down the definition, what's the set of all length t trajectories? They would say, well, it's a set of all u in Rm times t, all y in Rp times t, that satisfy a model equation. For instance, they exist in X, in Rnt, such that all of these together satisfy the familiar ABCD equations. This is one way how you can characterize that subspace, a set of all trajectories. You can also write down a difference equation or transfer function, whatever. Any of that is fine. So that's a parametric description. But you could also do this just by using raw data. Namely, you could just run your experiments and put all the experiments into a matrix. First column of the matrix contains your first experiment. Second column contains second experiment. Third contains your next experiment. Well, the system is linear, right? Linear means I can take two trajectories I've seen and I do linear combination, I get another trajectory. So it's not surprising that when you collect the row span of that matrix, or the column span, the image of that matrix, you get a set of trajectories. Well, it turns out you actually get the complete set. That is, you can just put all your experiments into a matrix. You take the column span of that matrix, and you get this very same set that will be spanned by a model. So this is too good to be true, right? I mean, it makes sense. It's very intuitive, right? System is linear. You take linear combinations. You again get trajectories. There's, I guess, an assumption missing. And here's the assumption. This is true if and only if this matrix is of low rank. Okay? That is, the complexity of that matrix essentially is the complexity of subspace you're searching for. So in total, I have length t trajectories. I have an input in Rm. So one part of the complexity that has to be degrees of freedom, number of inputs times length of time series, plus number of initial conditions. So the rank of this matrix, no matter how many columns you pile up, should be m times t plus n. For all t sufficiently large, in particular for all t greater than the lag of the system. And this is a very clean and powerful result, which now you could literally take any single result you've ever seen in linear system theory, in control, in filtering, information theory, and you could one-to-one replace the results that people prove known by models and use this type of description of your system. Instead of a model, you just use a raw data representation. And people are doing that. That's why it's like 2 or 3 papers every week on this topic, right? But the takeaway is, yeah, you can work with models, but equivalently, you can also just work with time series, put all your time series in the matrix, and the row span of that matrix is the behavior, the set of trajectories, provided that matrix is of low rank. By the way, you don't have to wait to the end to ask a question. If you already now want to throw in some questions, makes it more fun for me as well.
So if you have noise, you will simply have any recomposition and stuff.
Correct. So this is now the clean linear deterministic case, because any sort of noise will kill the low rank assumption, right? And you have to work about that. It turns out we don't do SVD, we do something else. So you can try SVD, but it doesn't work so well. Obviously, once you depart from linearity, from time-invariance, stochasticity, and whatever else, this will go away. This is only the nice, perfect equivalence. But people worked out the extensions. So that's, if you don't remember anything, yes, please.
The elements U11, U12, etc. They are not single samples, right? Like the basic.
They could be either one long trajectory that you just loop around. They could be time shifts of one trajectory, like a Hankel matrix, or they could be completely independent experiments. It doesn't matter. Any of that is fine.
An experiment is a set of samples.
Yes. So if you don't remember anything from today, just remember this one thing, right? That's actually enough. So you can work with models, or you just take data, and it's one-to-one equivalent provided data matrices of low rank. And thus you could now reinvent any result you've seen in linear system theory and do it this way. So in words, it says you can construct all trajectories you want to construct from previously observed trajectories. And maybe now you agree with me that this terminology that they called it themselves the fundamental lemma, which sounds very pretentious, is actually rather justified because it is a deep result. It turns out many things that people do implicitly rely on that result, like all of subspace systemification, signal recovery algorithms, motion primitives, dictionary learning, DMD, and all these things eventually rely all on this one equivalence that these guys have worked out. I should say when I found this original paper, it had like 50 citations or so, and it was all by the authors, meaning nobody ever listened to that result, but now it has a couple, I think approaching 1,000, so it got quite popular. So the result I told you about, by the way, was not proved by the behavioral people. That's a result that we proved. The behavioral people had their own version of writing things up, a little more convoluted and not readable. But literally, it's those guys that worked this all out, so we just cleaned it up. So it was Jan Willems, 2 PhD students, Paul Rapizade, Ivan Markowski, and Bart de Moor, who's a big guy in subspace identification. Their result was only sufficient. It had a bunch of further assumptions, which you don't need, but literally, it's their result. Proved, published in 2005, forgotten in time, and now was sort of resurrected. And as you can imagine, once you've seen this result, and it's so simple, so easy to grasp, people worked out all the extensions you can think about. They're very busy working out. So they extended to other system classes like bilinear systems, systems with block linearities, LPV, Volterra series, delay systems, whatever you want. They looked into other matrix data structures, and then by now there's like 5, 6 different proof methods to get to the result. So people are very busy extending this left and right into all directions and making it useful. So that's the main thing we'll build on and what we could do with that. So here's a bird's eye view on the literature. So this fundamental lemma got published in 2005. Nobody cared about it really. It was only the authors themselves, like Ivan Markowski extended a little bit to data-driven control. But again, this got like 10 citations or so until 2019. Nobody even knew that research. We sort of rediscovered it by chance in 2019 or so and used it. We proved the more general version you've seen. And then the literature already split up in 2. One part of the literature was going after explicit control design, like let's do H2, let's do H infinity, let's do Kalman filtering, let's do LQR, whatever, with these results. It's mostly work by DeePC and co-workers, all from Groningen. The other part of the literature went down the route of let's use this for optimization, let's use this for predictive control. And that's what I'll walk you through today. So what I'll tell you about is, how can you make this work for NPC? How do you accommodate noisy data? How do you accommodate nonlinear systems? And all sorts of extensions. People are still working on it today. Many extensions, probably at the CDC, you'll see probably a couple, 200-300 papers in any of these boxes. So there's a lot of them. It turns out when you talk to the old people, they always tell you, we knew it all. And it's true, actually. So when you go back in time, by now I discovered a bunch of work from the 90s, the 80s, even the 60s, where I said, oh, well, we knew this implicitly already. We just never cared about stating it that way. And so many of these things people do nowadays, you could actually work out from much older results from the subspace ID literature, from the adaptive control literature. So they had some of their own variations of this result, but not stated as cleanly. So that's sort of the little bit of a timeline of that entire field. So it really took off once it was rediscovered around 2019. So here's how we're going to use it. So I said we'll go down the MPC route. I could give another talk using it for the explicit controller, but let's do this. A little bit simpler to grasp. So here's the MPC problem. You are interested in minimizing cost function looking forward in time. That is, you have your model, ABCD matrices, and you run them forward in time. So index k runs from 1 until your horizon, say t future. And say you want to minimize, for instance, a tracking problem. So you care about your output y, tracking a reference with some weighting q, and while minimizing control effort. I mean, that's one variation of many others. And you want to meet constraints. Classic MPC problem. In Zurich, that's sort of the go-to problem of almost all industry. They replaced PID by MPC essentially. So people run this all the time on all frequencies, megahertz. It turns out when you want to implement MPC, then you realize, oh, that's that problem that everybody writes in the paper you cannot implement. Why? Because you need to initialize that recursion. You need to know the initial condition. If you don't know the initial condition, it doesn't make sense to write down these equations. You cannot start it. And there's many ways how people then recover initial condition to warm start these iterations. The simplest way is just, well, let's just use a model again, ABCD, but now the time index runs backward. So we'd have time k0, k minus 1, k minus 2. Essentially, you go backwards time until the observability matrix has full rank and you can recover the initial condition. So you just run the model backward in time until some time horizon t ini, typically taking roughly like the state order or a little bit longer, or the lag of the system. And there's many versions of doing that. Obviously, if a system is noisy, you don't want to satisfy these equations with equality design, but in a least square sense, like a Kalman filter problem. So that's the MPC problem. Again, MPC is a topic. Some people love it, some hate it, depending which school you sign up to. I don't necessarily have an opinion on it. Willems had a strong opinion about MPC. So Willems, the guy who invented the behavioral system theory, said, MPC essentially no theory and a lot of brute force. That was the statement. I guess he made it in 2007 when MPC was not so developed yet. But even then he acknowledged that, you know, it's the one aspect of the field where everything comes together. Control, estimation, optimization, computation, all in real time. So he was very fond of that part. But I agree with him, it's like a little bit brute force. You give the problem to the computer. What does the other side have to say? Well, let's not care about elegance. Literally, this is the gold standard of control. You cannot beat it. If your model is linear, deterministic, you know the model, this is the best thing you can do. You cannot beat it. Story over. Okay? It's just what you do. Now, of course, what's the catch? You rarely have a linear time-invariant system. It's rarely deterministic, and typically you don't know the model either, right? That's why in industry often PID is still used, just because PID you can tune without knowing the model very well. So it has some catches, obviously. So what I want to do now is let's replace the MPC by the data-driven control. And I just use the fundamental lemma. When you think about it, what are these equations doing? They're just describing for you the set of trajectories, the set of feasible trajectories you can optimize over. And I can use ABCD to describe that, or I just use my fundamental lemma and say, these trajectories must be in the image of my data matrix. So that's the data-enabled predictive control. It goes as follows. It's the same problem as before, same equations. The only thing I did here, I replaced ABCD by saying the trajectory I'm searching over has to live in the image of a trajectory matrix. So in particular, in this matrix H, it contains all the data that for now I collected offline, UD and YD. And I say any trajectory I want to optimize over, that is my future U, my future Y, as well as when I go back in the past, which I also have to do for the initial condition estimation, so the most recent outputs Y ini, the most recent inputs U ini, that entire sequence, that is one trajectory, that's the one I'm optimizing over, that has to live in the image of that trajectory matrix.
So U ini and Y ini are part of the data?
Yes, so U ini, Y ini is your real-time measurements, so your last n measurements that you collected online.
So the decision variables are U, Y.
Correct. And she collects the columns of that matrix. Okay. And the trajectory matrix I now collected from offline data. You can also adapt this thing online if you wanted to, but now let's do it just offline. And that was actually already it. This is like, took not very long to work this out. You just replace A, B, C, D by your fundamental lemma. Your trajectory you optimize over has to live in the image of the trajectory matrix. So you can very easily show that this is perfectly equivalent to MPC in the linear deterministic case. That is, the feasible set of this optimization problem is one-to-one the same feasible set as for the MPC setting, and you get the same solutions. Okay? In the deterministic LTI case. Now this, as I said, took like 2 hours to work out and write down, simulate it, and so it works. What we're a little bit frustrated about is like you put a tiny bit of noise in the problem, just like an epsilon bit of noise in your data, and all of this breaks apart. It doesn't work anymore. So it's, as of now, it's just a theory result in the perfectly clean setting. If you have linear systems without noise, then this works out. But otherwise, you somehow need to robustify this thing in the setting of noise and nonlinearity, which is what the talk will now be about. How do you make this thing work when your data is not clean? But this is like the main idea, and as I said, this you can teach to a bachelor student, right? And make them applied. So how do you work? What do you do when you have noise and nonlinearity? Let's go first for the setting. The simple one is, say you have measurement noise. That is, the reason most measurements that you collected are noisy. Well, what you do normally, you run a Kalman filter that filters out noise. You solve a least square problem. What's the Kalman filtering version here is you add a slack variable sigma, and you solve for the solution with the least slack. So you penalize the slack. Essentially search for the least square solution. Okay? Essentially, it's sort of a moving horizon filter, like a Kalman filter, with some coefficient lambda y in front of this penalization. If you make lambda y large enough, this will very nicely work out for your least square estimate of this equation.
The stack is only in the initial data, not in the
That will come. Give me 1 second. But you're right, this is not just for the initial data. But as your colleague here pointed out, the much bigger problem is the following. That is, if your data is not coming from an LTI system, and it never will, it will always be corrupted by noise, it will always have nonlinearities, this matrix will have full rank. Now think about it, if this matrix has full rank, then any trajectory you wish for lies in the image of that matrix. In particular, the trajectory y is equal to r and u is 0 lies in the image of that matrix, which means I solved the optimization problem down to the global minimum 0, but that doesn't make any sense, right? So obviously, once your data is noisy and nonlinear, this entire setup completely falls apart because this constraint is not active anymore. You can search for any u, y, and g essentially. So how do you go about this? It turns out we need to make sure we only take the reasonable choice of columns of that. So what we need to regularize the g variable. The g variable collects the columns of that matrix, and we spend a lot of time working out different regularizers that I want to tell you about today. So let me first give you the high-level perspective, what you might do. So you may say, I come from signal processing or machine learning, statistics, or whatever, and I use a Bayesian intuition that tells you what is a good regularizer, like I want to promote sparsity or whatever. So you could say regularization should incorporate a prior assumption. For instance, the prior assumption could be, well, this matrix is of low rank. Well, if this is a matrix of low rank, then I just need a sparse G to get away with a solution. So maybe I put as a regularizer here a one norm that will promote a sparse solution. Okay? So essentially, it's a surrogate for making the matrix low rank. Okay? You suggested before we could also do an offline SVD. It turns out it doesn't work so well. So we tried this many times. If you do first a pre-processing of the data, like an SVD type fitting, the results are typically worse.
and it's not sparse either. SVD
It's not correct. It's not sparse. You get a low rank property. But so our objective is to stay as close to the data as possible. Don't do any offline pre-processing because ideally the goal is to make this, of course, all real time. Okay? So this could be one possible regularization, say, incorporating the low rank assumption. I'll make this more precise later. If you come from operations research, you may have a very different perspective on what you should do. In operations research, when you say, I'm confronted with a noisy problem, I need to robustify it. Okay, so if I want to solve something like a least square problem, minimize ax minus b, yeah, I can do this. The solution is given by x is the pseudo-inverse of a times b. That's easy. But now what do you do if your A is noisy or A is uncertain? Like here, you have an uncertain matrix if you want to. So you have an A plus delta. Well, how do you make sense of that problem description? So an operations researcher would say we need to robustify the problem. So what we should solve for is either some expected value type problem or a robust version, for instance, a min-max problem. You say, well, don't solve for the min, also do a max of all uncertainties. For instance, a max of all perturbations delta lie in a norm ball of radius rho, for instance. Okay. So now we'll do a little bit of math, but the math will be just a triangle inequality. It's not hard. So one way to go about this, say, well, this problem, I don't want to know how to solve it. Let me just apply the triangle inequality, because there's a sum inside a norm and split up in two terms. So I have a min-max over ax minus b and delta x. Notice this triangle inequality is actually tight. It holds equality because I can always choose a delta in my uncertainty ball to make these vectors collinear. So it actually holds with an equality. Now solving the second problem is trivial. The max of all delta less than rho of delta x is just, well, rho times x. So the entire problem boils down to just solve the original least square problem plus a regularization. Meaning regularization also accounts for a robustification. So it's two different paths leading to regularization and why it makes sense. Once you understand these tricks, you can do this in various forms and colors. It doesn't have to be this nice norm ball. It can be anything else. Typically, the math always goes the same way.
And this works better than total least squares because you have uncertainty in the B as well.
Yes, it works better. I mean, we tried all sorts of these variations, also total least squares, low rank approximation, and so on. So we found that adding regularizations was the best way to solve the problem. Yes, please.
You mentioned some way of dealing with noise,
Uh-huh.
but you're sending that noise to the outputs.
So there's two sources of noise. One is in the outputs. The other one is inside that matrix.
Yeah, that would be my question. The process noise is accounted in the matrix.
It's in the matrix, yes. I mean, you could also think about noise on your U if you want so. You have input noise you don't know. You could also add a slack variable here. Could be done. But what we find, these two tricks are normally enough to solve the problem. So that's sort of the way to make this robust. I'll spend some more time later explaining more in detail how we pick those. I mean, this was just like some pocket player tricks that you know the tricks of the trade. You could easily derive those. We'll make it a little more rigorous later. So it turns out since this formulation got invented, people have thrown this in all sorts of case studies, and these are all like real-world implementation. It's not simulations. It's putting it on the real deal type thing. So we put in all sorts of control problems on power converters, on drives, on even the power system. So in China, part of this we try on the power system, the real system. People in robotics use this a lot, especially in soft robotics, where you don't get good models. So you need to work with data-driven descriptions. My two favorite applications I've seen where people use this, one, I've seen a few applications where they use this for growing plants. So apparently there's a hot business and a good business case in startups to be had when you want to automate greenhouses. And growing plants, you don't have nice models. And so they use these type of methods, among others, to optimize for tomato growing. Apparently it works. Another interesting one, I just got that 2 weeks ago from colleagues in China. They use this to do closed-loop diabetes control. So artificial pancreas, so insulin injection. People have been trying control methods on that for 2 decades or so. The main challenge there is not to control, it's getting a model. And it turns out, well, using these methods, you don't need a model, and they apparently work pretty well. So now actually running animal trials. So it's already on, not on humans, but at least on animals, they essentially run this algorithm to inject insulin. So maybe takeaways, this is very simple. Like this is nothing complicated, but it works extremely well in all sorts of situations where it's hard to get models. Good. So now we'll step up the levels. Now we look a little more behind the scenes. Why does this work? One is the notion that regularization incorporates prior knowledge. In particular, it does some sort of hidden system identification. You never aim for a model, but it turns out what the regularization does for you, essentially, it's creating a model. So here's one of them. I told you you can do a low rank approximation, essentially by doing a one-norm regularization. Let me tell you how this works. So let's go back to our bi-level description, where we say, let's first learn a model, and with the model, we do control design. One way of model learning in subspace system modification would be the following. You say, well, I see my data UD, YD, and now let me find my closest approximation to the data, U hat, Y hat, such that this approximation is low rank. Okay? So if you were just to solve this inner problem alone, and you make some idealistic assumption, for instance, then total least squares or SVD would solve that by itself. Okay? So low rank approximation. And then you go with that into your optimal control design. Optimal control is stated as, well, now that you have cleaned up your data, you can just say a search for trajectories in the image of my data matrix. So it turns out you can rewrite this entire problem and turn it into just a one-norm regularization. Let me show you how. And again, this is nothing complicated, it's just a sequence of little tricks. So, well, since this problem has the property that this matrix here is low rank, this is low rank, I can always find a sparse solution. So G is sparse. So I could say the zero norm of G is less than ML plus N, which is the rank of that matrix. I did not change the feasible set. It is what it is. No changes. Well, now let me do a convex relaxation. Say, I don't like rank constraints. Rank constraints are hard, non-linear, non-convex, non-differentiable. Let me just cross it out. I just throw it away. I search for a regularized solution. Okay. If you do that, then this upper problem has this inner problem is a unique solution. And the solution of this problem is just, well, U hat is UD and Y hat is YD. So you get to this solution. It just reduces to that problem. So now, with that convex relaxation, now showed, well, instead of solving this full problem, I can solve this problem where I look for a sparse G. Now, sparsity constraints are hard. We don't like them either. So let me do a one-norm relaxation, replace the zero norm by a one norm. I lift the one norm up from the constraint to the cost, and we get just to the one norm regularization. So essentially what the one norm regularization does for you, it essentially constructs your low order basis. It does a convex relaxation of the rank constraint. Okay? And it works very well. So it's why does it work well? It turns out when you want to identify a system, anybody ever worked on real data and tried to identify a system? The hardest part of system identification is what is called model selection. That is, you need to choose your state dimension. Like when you get real data, the real data will not reveal a nice state dimension. And so the hardest part of sysID is to choose that n. Turns out this is sort of a smoothened version. You don't choose a state dimension, but you promote it softly by choosing a regularizer. You're the perfect person because I always have the answer for you in the next click. No, that's great. That's great. That's also good for me because then I chose the right storyline. So obviously now the problem is you need to choose this lambda sub G. If you just throw this on a system, whatever you want, this is the typical curve you get. Like what you plot here is the realized closed loop cost when you run this in MPC fashion. And now you need to tune the lambda. And what you normally see, well, when you don't regularize, you get bad performance. You start regularizing, you get down to a nice valley, and then you over-regularize. Essentially, when lambda G is too large, you search for a zero solution here, which is also not good, and it goes up again. So that's something you have to do. Is that hard? Well, I mean, look at the axis here, and that's quite representative of almost all systems I've seen. This plateau here spans from, I don't know, 10 to the minus 1 to 10 to the 4. Meaning, in practice, you just choose, whatever, you try 10 to the minus 3, 10 to the minus 2, 10 to the minus 1, and so on, and you will land very quickly in that plateau. So tuning this is typically just 1 or 2 tries, because that plateau is very wide. But yeah, you need to choose that one carefully. Here's another regularizer that works extremely well, that also sort of comes from subspace identification, or we invented it to reverse engineer subspace identification. So in subspace identification, you would say, well, there is a subspace, let's call it K star, that tells me how is Y related to my U and my past data. Okay, that's all what subspace sysID is about, finding this linear predictor if you want so. One way to find this is just by solving a least square problem. Let me introduce some notation for that. So normally partition your data into 4 blocks. One is the past data, one is the past outputs, or past outputs, past inputs, past outputs, future inputs, essentially be compatible with Y is YF, U is UF, Y ini is YP, and U ini is UP. That's sort of the standard notation they use. You just partition your data in 4 blocks, and then you just solve a least square problem. That is how any subspace system application algorithm works. It says, let's find the subspace predictor here by minimizing a least square problem where you say, I want to relate my output data to my input data and my past input output data through that predictor, and you find it. Okay. Very classical, going back to the 80s. Used everywhere on your MATLAB implementation. You can solve this problem very easily. The solution to that is something called SPC, subspace predictor, or subspace predictive control. It turns out the closed form solution is just, well, YF times the pseudo inverse of that matrix. And people have agreed on, for a linear system, this is maybe the best predictor you can find, unless you want to incorporate here further assumptions like causality, low rank, and so on. But if you don't incorporate that, this is the best thing you can find from the data. Used probably in almost any industrial control application where people were interested in finding a model. It turns out, if you think this is a good way of predicting things, you can recreate this in the DeePC. That is, now you choose as a regularizer here, not a norm of G, but a particular projected norm. In particular, you project here onto essentially the image of this matrix. It turns out the solution you get when you choose the projection orthogonal to the kernel of this matrix is one-to-one the same. Okay, so if you think this is a good solution, you can actually now choose a projected regularizer where you can write this down explicitly as a function of your data, and you recover that solution. It turns out you can choose any norm. The norm doesn't matter.
For orthogonality, probably need the two norm.
Yeah, I mean, where this projection comes from, you normally write down something like this matrix times its transpose or so, but the norm you put here will not make a difference. I mean, if you minimize that in one norm, two norm, or whatever, this will be the same. It turns out this regularizes a very nice property. That is where I told you, like, norm-based regularizers normally show you, well, when you look at performance, plot the regularization coefficient, it goes down. It stays down there for roughly like 2 or 3 decades, and then goes up. Turns out when you have a linear system, you actually go down and you stay there. Just because for a linear system, this is the best thing you choose for. Meaning for a linear system, if you use this particular norm-based regularizer, you just need to find a sufficient large coefficient. They don't have to find a sweet spot. Even better, you can even find this a priori. So if you go into the statistics literature, people developed heuristics, how you find the optimal regularizer. In particular, one that's called Hanke-Rouse heuristic that tells you a priori as a function of your data how you should choose your regularizer to get the sweet spot. So now this method is completely hyperparameter free. You can just apply it. In the case of a linear time-invariant system. So let's see how this works. So I like the power system, power electronics applications, personally. I think they're very meaningful. So here's one study. You can throw this on a wind turbine. Okay? So wind turbine consists here of the mechanical part. You have your power electronics. Inside here, you have your control architecture power electronics. You're connected to the grid. Okay? And if the transmission line is very long and you use here something like a phase lock loop type algorithm, it turns out very often you get here unstable oscillations or sustained oscillations, which cause lots of havoc all over the world, like in Europe and China and the US and England. There's a lot of so-called subsynchronous oscillation, create a lot of trouble on the grid. You could easily dampen these oscillations if you had a model. But here's what, in the power, so biggest assumption in power system is you have a model, but in reality, nobody has a model of a power system. Because the models for this one is with the company that built this wind turbine, like Siemens. There's another company maybe that does the electronics, like Schneider, Hitachi or so. And then there's the grid operator. None of these share models. I mean, they have models, but they don't share them. They don't share models of data. So in practice, the person has to control these things, has to do this essentially black box, because you don't have models. Okay? And so how can you reject these type of oscillations in a model-free way? And there's now roughly 30 states, nonlinear, 37 states. So here's what it looks like. You see an oscillation. You start probing your system, meaning you inject in your converter controls some probing signal. You collect your data here for about 2.5 seconds. If you were not to do anything, you see these oscillations would grow unstable. They're also non-harmonic, so they're nonlinear. But if you throw DeePC on that, with any of the regularizers you want to pick, they all work well. They would all dampen these oscillations very nicely. Okay, now this is a nonlinear high order system, and it works just out of the box very well. Again, tuning the regularizers, here would be the three different regularizers. They would all show this behavior, but you can easily identify the sweet spot a priori. You don't need to tune it actually by hand. You can use these heuristics. So that's now 37 states. This is by now implemented and running in Inner Mongolia and China to dampen oscillation, so it works nicely. You can scale this up. Let's see, 37 states is fine, but can we go to hundreds and hundreds of states? And so let's take an entire wind farm and a power system. And now you maybe appreciate nobody will have a model for this thing anymore, but you still want to use the wind turbines to provide some sort of meaningful response to the power system in case if a load loss frequency drops, you want to stabilize it. So here would be the plots. If you run the DeePC on that wind farm, again, completely model-free, there's a fault on the grid, frequency would drop, eventually recover and be stabilized by the generators here, but you want to assist them. If you were to identify a model, like with subspace ID, it turns out, well, what you do, you eventually do something, but it's not very useful. Whereas again, the DeePC with any of the regularizer would work very easily and efficiently. Okay, and it doesn't need a lot. Like a graduate student can implement this and run this. Yes. So we need to get it down to like roughly 10 millisecond sampling time. Yeah. Well, this is a simulation. No, this is not the real. I mean, for the real grid, I cannot share the data. But for individual wind turbines, we also connected it to the real grid. Yeah. It turns out what the data-driven control did was something very clever. Like you see frequency dropping, I mean, there's a loss of power in the grid. Where you get the power from, where if you know wind turbines, there's a source of power, namely your blades. There's kinetic energy stored in there, and you can suck kinetic energy out of them. And that's what the data-driven control did. So it would steal some active power, so really energy, from the rotor speed. So it would deload the turbines, they run slower, and that's where you get the power from to stabilize the grid. And again, we didn't tell the algorithm that, it figured it out by itself, which I found quite amazing. It's nice. So again, takeaways, this is super simple. Like it's nothing super complicated, right? But it works extremely well. Now, this was already a nonlinear case study. But you've seen in the examples I showed where people applied this left and right that they applied it to many nonlinear systems. And people worked out extensions of this to nonlinear systems using basis functions or whatever. But basis functions typically make the problem very large scale and not implementable more in real time. So I found a very pragmatic view works best, in my experience, for this problem. And the pragmatic view is very naive. It says there is no nonlinear system. And that's actually a mathematical theorem. Like every nonlinear system, under very weak assumptions, you can write as a high-dimensional linear system. Right? There's various tricks like Koopman operators, Sturm-Liouville, Volterra series, Flies, Kaleman linearization. They would all embed a nonlinear system into a high-dimensional, typically infinite-dimensional linear system, sometimes at the price of bilinearity, which has its own issues. But if you go the data-driven route, that says, well, everything is linear in high dimensions. So let's just run with that assumption. Meaning, let's just collect data, let's make the matrix as big that we can still solve the problem in real time, and then let's use our regularization to figure out what are the relevant features. So let's not otherwise do it. It's very pragmatic, but it works well. Let me just show you how comfortable we are. That's a nice example actually for today, for this building. So this building, I would guess, maybe a little more than 100 kilowatt power consumption. So we put this on a 100 kilowatt inverter. 100 kilowatt literal meaning all the power absorbed by this building goes into one set of switches that go up and down all the time. So it's something you appreciate is very delicate if you want to control it, right? Very tough to be under state constraints, also some nonlinearities. So we sent a graduate student there to an implementation lab in Munich and asked the graduate student, well, could you implement this there? They gave us permission. And it literally just took him 2 hours to operate this thing. So he collected data for 2 hours, and then he could run this type of stuff. He could jump up from 0 to 80% in the operating range without overshoots, essentially perfectly. No model at any time involved, which was quite amazing and sort of tells you how comfortable we are in this method, despite that system being, very safety critical, obviously, and nonlinear. So it works unreasonably well. Like really unreasonable. I was very surprised whenever I see this type of stuff when people make it work and you wonder why. And that goes back to this argument that regularization makes you robust. So I don't claim to be a nonlinear method. If you want to do something like fly a backflip for a quadruplet, this will not work. But it can be robust to reasonable nonlinearities. So here's what took us then more than 2 hours. That took us like 5-6 years to develop. It's called distributional robustification, which when you come from image processing or machine learning, that's sort of the robustification you care about. It goes as follows. In an abstract setting, what we want to solve is minimize an optimization problem depending on the decision of X and depending on data, okay, where the samples represent your model of the world out there. Xi hat are the samples. Now, the way you solve this normally, you just take the empirical distribution. So you could say, well, instead of calling Xi hat samples, let me call it a random variable and solve for the expected value of the random variable. All I have is samples, so my best case for the random variable is I just take the empirical distribution, putting a delta everywhere. Which makes this look like, okay, you can solve it this way or that way. This looks harder. But let me tell you why this second viewpoint is interesting. It's interesting because this distribution, p hat, your sample distribution, is a very, very poor estimate of the real distribution out there, of the real nonlinear stochastic process drives you. Okay? So you get typically, if you solve this problem, very poor out of sample performance, so the famous out of sample loss, because you solve for the average solution. But the real problem, yeah, your data comes from some distribution, like the nonlinear stochastic process driving the world. But you don't know this other distribution. All you have is samples, but you don't know the real distribution. So what you should do, you should robustify yourself to this distributional uncertainty, to not knowing what the distribution of the real world is. That's called distributional robustness. So you'd like to find a problem formulation, not this one, but one that says, I'd like to account for all possible stochastic processes, linear, nonlinear, Gaussian, non-Gaussian, whatever, they could have generated this data. I'd like to be robust in that setting. That's called distributional robustness. Robust to all sources that could have generated data, among others to nonlinearities. So if you want to write this down, you have to solve something like a min-max problem, mathematically precise inf soup, where what do you do to the max over? You say your random variable comes from a distribution Q, but you don't know this Q. You know the Q should be somewhere near your samples, but that's all you know. So Q should be in an epsilon ball related close to your samples, epsilon close to your samples. And the devil is, of course, in details. How do you write down this ball? And what we found worked best is something called the Wasserstein metric, optimal transport type metric. You can look at the formula, but maybe it's easy to look at the picture. So you would like to figure out what does it mean to be epsilon close to your samples? What is a reasonable distance measure on distributions for this problem? So when you look into these two distributions, like this is the, for instance, real one, this would be a samples, I'd like to understand how far are these away from each other. And what a literal measure is, how much effort does it take to shovel over this dirt pile into that dirt pile? How much do I need to pay to bring this particle over here? So I take the difference of Xi hat minus Xi in some norm, say some p norm, and then I integrate over my joint distribution. I integrate over the joint distribution, pi, you know, that covers this and that. It has these marginals. Now, of course, there's a lot of distributions that have these marginals. So you take the smallest one of all of those that has these marginals. Like find the smallest way to shovel this dirt pile over to that dirt pile. So as you can appreciate, while this maybe makes sense, like you want to account for all distributions that could have generated data, like good luck making sense of this stuff. Like even just parsing it, what it means, and let alone solving it, seems very hard. Because it's like a doubly infinite optimization problem, infinite dimensional. But it turns out people in operations research have worked very hard and just in the last, say, 6-7 years, figured out how to write this as a finite dimensional convex problem. So this is now solvable. It's not, you don't need to go to function spaces or distribution spaces, but you can solve this. Particularly one result I like very much, they worked on the following. So you want to solve this distribution robust formulation, like min-max, where you maximize all epsilon nearby distributions, where nearby means in this particular norm ball in distribution space, so p norm here. So they worked out that this is equivalent to solving your sample average problem. So you just solve the problem with your samples plus a regularization, where what you put in front of the regularization is epsilon, that is how robust you want to be, a Lipschitz constant, and what you choose here is a dual norm. So a dual norm of p. For example, You want to be robust here in an L infinity sense, L infinity in a space of trajectories. This means you have to put an L1 norm here. Okay, and so you can derive an entire different set of good regularizers this way that tells you, oh yeah, that's the reason why I'm robust to distributional uncertainty. That's why I'm robust to the data coming from a nonlinear system, for instance, or at least weakly nonlinear. Right? It also explains these curves. What does this epsilon mean that you put in front here? It tells you how robust you want to be. If I'm not robust, it doesn't work. Then I become very robust, and then I'm suddenly robust to everything, and it doesn't work anymore. So it's another way of looking at these problems and a more principled understanding why this works for, let's say, weakly nonlinear systems. There's many, yes?
In the previous slide, could you use the Kublai-Leibniz difference between the distributions?
No, you cannot, for the one simple reason. Kullback-Leibler requires the two distributions to have the same support set, meaning I just look at other distributions which are supported on the same samples. Whereas here I can compare a discrete distribution, samples, with a continuous one. Kullback-Leibler would not allow to do that. Yeah. So this sort of, at least for me, a very good justification why it works for nonlinear systems. There's many more things people have done, we have done, others have done. Like you could tune this from data, what's your epsilon? You can do this for constraints if you want to. And there's many further results that would take an entire PhD course to tell about, like more structure on certain sets, closed loop data, and then end and end. But I think we're all waiting for coffee. There's a white elephant in the room. Who sees the white elephant?
You can replace all this, Jung's work and so on with this.
You think you could. Correct. How does this compare to society, right? Because can you always beat society? It turns out in every single experimental application we have done, we always beat society without exception. But there's also some way you cannot beat it. And so where's the line? When would you do society? When would you do that? Yeah.
What about if you're interested in the parameters and the bias?
Ah. I'll get to exactly the bias. But perfect question, thanks. You're the best student to have. So here's, it goes to the bias variance trade-off. So when you should use one or the other, right? It's not always use one. Like you never have one solution that always wins, right? There's obviously, it depends. And the dependency depends on the bias variance trade-off. So recall, the model-based indirect approach is find a model from your data. The model belongs to a certain class, like has some complexity parameters like state dimension and lag. Once you have the model, you go into a control problem, model-based control. So the inner loop is the identification, the outer one is model-based control. Here you can see very clearly what identification does. It takes the data, okay, and it projects the data onto a predictor, a model, that comes from a certain model class. Okay? What does it do? By doing that, essentially cleans up the data. It makes sure that after doing this projection, what I have here is not noisy anymore. So it removes variance from the data, it shaves it off. But also, this is very bad if you choose the wrong model class. That is, if your plan, say, is not linear, it does not have a state dimension n, it does not have lag L, then you get here a bias error. That bias error carries forward into your model-based design, and when you implement it in closed loop, you may not recover from the bias error. So that's the disadvantage. Whereas what the direct approach does is the following. It doesn't do any inner model selection identification problem. It just looks for trajectories consistent with data, and it adds these regularizations. And these regularizations should essentially replace these things here. Meaning, there's no denoising going on here. So you don't shave off noise. You just take the noise as it is into your problem. But also there's no bias. Okay? So the regularization robustifies the prediction. And sort of you can think about it as a trade-off in terms of this does the identification, this does the control design. But clearly here you don't get a bias error. Okay? So takeaway is the following. Identification wins. This classical approach wins when you know your model class. When you know your model is linear and you know the state dimension. And the only source of uncertainty is stochastic noise. Then you cannot beat this. This will be the best. However, when your problem does not fall into these neat assumptions, That is, when you don't know your model class, so you don't have linearity, then the slow approach can actually win. And it turns out in practice, it almost always wins. Okay, so sometimes it pays off not to go through the model route. It's a little bit unfair to comparison because the regularization also does a robustification, that is a robust design, whereas here there's no robust design. If you were to figure out how to take the uncertainty from here and put it into the control problem, you could also robustify yourself. But that's sort of the comparison. If you know your model class and you only solve uncertainty is noise, then identify the system. If you don't know it, this may actually win. I had that argument with Leonard Jung, and he agreed, luckily. But yeah. So it can beat ID, and actually in practice, it almost always does it. And it's definitely much easier than identifying a model. Okay, do we still have energy, or should we go for coffee? Tiago, what do you think? Sure? Okay. So I can tell you three more slides about the recent extensions we've done that are less worked out. Because if you think about it, it was essentially everything was linear LTI. Everything was LTI deterministic, this fundamental lemma, and then I added a bunch of essentially robustifications around it. So on top of it, I put a robustification, which is good and nice, but it somewhat, as a scientist, bothered me in terms of, I would like to do this more principled. Can we do this bottom up? Can we develop like a behavioral system theory for stochastic systems, where your system is not a set of trajectories, but a distribution of your set of trajectories, and work with some bottom up thing like that, and see if this is any useful. So that's something we're busy on understanding now. It turns out it will not necessarily need two new algorithms, but it will give a different perspective. And one thing I learned, it all depends on the definitions you make. Everything, the entire house of cards falls apart with the definition you make. So if you think about Willems, a famous quote by him is, the behavior is all there is. That's sort of his viewpoint. The behavior is all there is, just work with data or trajectories. The next abstraction was choose inputs and outputs, maybe add assumptions like linearity or subspace property. Then say, do you go for multi-step predictor or recursive model? Do you want to incorporate time variance, low order causality? And eventually get to things like ARX, state space, and impulse response matrix. And you can find your way anywhere between here and here, right? One thing that we learned and understood in the last 6 years, in the entire story I told you, maybe it doesn't make sense to go all the way over here. Maybe just taking inputs, outputs, linearity, and maybe going for multi-step predictor is actually enough. We see it working better in almost all cases. So one thing we learned, at least in this LTI setting, is well, you should not go all the way over here and incorporate all these stuff. But maybe what is good enough is just having anything that from your data would do a time series prediction forward, incorporating linearity. And that was good enough. So then rather than defining what stochastic system means over here, let's define what a stochastic system means over here. And the very simplest case, and I apologize, this is very naive, but it does the job. Let's just add Gaussianity on top of it. Let's just not search for a subspace, but let's search for a distribution which is centered in subspace, and then there's some variance around it. Okay, so we have a Gaussian type of behaviors. So here's the definition we use. It's very naive, but essentially it just says that plus Gaussianity. Say trajectories are distributed as a Gaussian process. Full stop. That's the definition. The Gaussian process has some mean and some variance. And the mean is the subspace. Okay, so very, I would say again, naive definition. But we chose that deliberately because we saw it working so well in the LTI case that we don't have to go all the way over here, but this is actually good enough to work with it. What does then in this setting identification means? Identification just means collect data. From your data, construct the empirical sample covariance matrix. And that sample covariance matrix should give you that. And the mean should give you that. This sort of identification at this level of abstraction. What does prediction mean? Prediction means you take your full Gaussian behavior over your trajectory space and you do conditioning. So I now take y conditioned on my initial data and my input. And when I do this, and this is a Gaussian, I get another Gaussian. This Gaussian has some mean. The mean will be a matrix times u in y in u and a variance. Fun fact, this matrix you get here is exactly the same matrix that people from the subspace world would have also identified. It's the subspace predictor, like the pseudo-inverse of this UP, YP, UF, and so on. Okay, so again, a thing you've seen. So this naturally just comes out of here, which told us, well, if this very naive type of setting already gives us the right predictive distribution in terms of the subspace predictor and some more complicated variance, then maybe this is a good thing to do. So what we're doing now, we run with that definition. We don't make it any more complicated. We stay at this very naive level and see what we can do with it. So special cases. So now our perspective is, we have a conditional distribution identified from data that tells us how does y depend on the immediate past and on the input u. And you can now think about solving different problems. Say, let's first do certain equivalence. Let's solve the expected value problem. So I solved the control problem, minimize the control cost over u and y with an expected value over my trajectory distribution. So this gives you actually, again, subspace predictive control, just SPC. That's stuff people have known in the 80s already, but you can get it from here. You can again be distribution robust. They say, let me solve here something like a min-min or min-max problem. Let me just put up both here. So you can put min-min or min-max. So control people always solve min-max. When you work with reinforcement learning people, they always solve min-min. Again, a big cultural difference, right? Reinforcement learning is always optimistic in the face of uncertainty, min-min. Control people are conservative, we go for min-max. So if you solve the min-min problem, so now of all the distributions you identified, you say, well, let me take the distribution that is close to my data. So that's the one that comes from my data. But now I say I want to optimize over all distributions which are close to my data, close in this case in a KL sense, because now we are in a Gaussian setting, we can use KL. So I choose now the expected value from all nearby, and I choose an optimistic way. I write the min-min. It turns out then you get exactly the DeePC with the norm-based regularizer. So again, recover something we knew before. What we didn't know before is that DeePC is actually the min-min solution, which we found interesting, because I would know how to drive it as a min-max problem, but also it's a min-min solution. You could also solve the min-max fashion and say, let me take the min-max and I maximize over the expected value of my predictor, subject to I'm nearby to my identified expected value in a KL sense. This is a new formulation people have not made up yet, but it turns out you can convexify it, you can solve it. It turns out it's not very nice to solve it because you need to go all the way to a conic program, which probably will not be able to solve in real time, but it's in principle solvable. If you look at the plots you get, say you want to have now a stochastic system that should do something, and here's a constraint that you shouldn't violate, or you can only violate with a certain probability. If you go for distributionally optimistic, so you solve the min-min problem, it turns out the solution you get from this min-min will go very close to constraint, actually closer than your identified distribution. If you solve the min-max problem, it turns out the identified distribution will always be closer to constraint than your one because you're conservative. So I guess it's the difference of max and min, how close do you go to constraint. So you can recover a lot of the old friends that we've known from other derivations, but also new ones. What I'm very excited about, and we have not fully understood this yet, is the following. Your model now is not a deterministic model. You now have a model that says, just go back here, your model says you have a distribution over trajectory space, meaning your model has a mean and a variance. So you don't say this is my prediction, but there's an entire set of predictions. And can you make sense of that? So can you use that to reduce variance? So when you look into what you predict, which is the blue curve, and what is realized, which is the green curve, there's always a mismatch, and deliberately so, right? Because your model has variance. And all these errors are correlated with some distribution. They're correlated in time. And then the idea is, can you actually use the fact that your predictor has a variance and use the fact that you can measure this error? Because this error is just my prediction minus my realization. Can I use that to reduce variance? Which in the optimal control literature is a quite classical setup. They would say, let's do what they call disturbance feedback. That is my U that I search for is a feed-forward solution, the one you get from MPC, plus a feedback on the error. And the feedback has some triangular matrix, some causality properties, but essentially just feedback the error into your optimization problem. It turns out when you do this, you can work out your predictive distribution will be This would be just your subspace predictor. That's your mean. That's the one we've seen all the time. But then you get an extra term that tells you how you can control variance. And that mu is a particular part of your predictive distribution. And here's your causal feedback law. And you have the natural variance anyways. That's the identity term. That's this one. But now when you choose this cleverly, you could maybe shave off some variance. And now the idea is, well, can I optimize both over my feed-forward solution, this one, and can I optimize over the feedback on the stochastic noise? Turns out you can write down the problem, you can convexify it. Let me just show you the results straight. So here's a very preliminary case study, just in simulations. There's a very classic example from tube MPC. So a bunch of disks. You apply a torque here. You want to control some angle there. If you just do certain equivalence control, you see your outputs go up with big variance. That's your control input. It's deterministic. But when you do this one, where control input depends on the variance, on the error, it turns out you can actually narrow down this tube. Okay, so you can reduce variance. Price, of course, the controller itself is now stochastic. So now you have a random controller, but that randomness allows you to get rid of randomness in the system, which is quite nice. That's our level of understanding now, but this is one of the frontiers we want to push in this DeePC world. Really at the end now. Takeaways. If you don't remember anything, just remember this. You can use just a matrix time series as your model. And you can do anything you want to do, like any sort of control design with your matrix time series. We use it here as a predictive model. However, this only works in the ideal case. You need to robustify it with, in our case, regularization. It's a very simple method. It's, almost embarrassingly simple, but it works very well, which is a good combination. I guess we've been very lucky to find it. In terms of ongoing work, I'd like to make this adaptive, like collect data in real time, refresh my data matrix, see if I can do this. Turns out it's very hard. With plenty of heuristics, but no results, to be honest. Go to more complex system class, of course. But what I really care about is not so much the theory. I really want to understand the applications to a business case, like applications where you say, this is where this stuff works, but nothing else would work. Think about stuff like soft robotics or so, where you don't have models anyways. So that's what I mostly care about these days. What you should have asked all the time, but you didn't ask it. What's the catch? Yes, there's the famous no free lunch theorem, right? The catch is the following. Compared to models, you have to work with a full-blown data matrix here. This data matrix is not sparse. It does not have interpolate structure. There's nothing recursive about this. Like all the things that models have when you write this as an MPC constraint, that doesn't have. So it's no sparsity and essentially more real-time computation. So my experience is compared to solving a model-based MPC problem, computation time goes up by a factor 10 to 100, roughly. So it tells you really what are models good at. They're compressed versions of your data, they're denoised versions of your data, and they're tidied up. Whereas this is essentially a mess in this regard. But that's important to highlight, that's not the one-fits-all solutions. There's the catch. Good, thank you.